and welcome to another video on my channel. Today we will be talking about the applications of integral calculus and just a lot of stuff related to integral calculus and a little bit of talks about what's to come next and also a little bit of talking about the applications that combine both differential and integral calculus. Without further ado, let's go to the next slide. The first topic we're going to cover is area and volume. The fundamental concepts of area and volume, that is. So, of course, the area under a curve is the integral of f of x dx. Now, the area between curves is f of x minus g of x, then all of that dx. Now, this shows the area between two different curves on the xy plane. Now, volumes of revolution is a little bit different. It's where you have a 2D shape and revolve it around an axis to create a 3D shape, and then you figure out the volume using the disk and shell methods. And also, there are irregular shapes, not like irregular shapes like polynomials and stuff, but like different dimensions and like third dimension or even higher, which are called complex geometry. There are some applications in the same area's field. So, the first application is the consumer and producer surplus in economics. So basically, we're trying to see the economic benefits of a certain thing using the areas between the curves for the price and everything else. Now, probability distribution in statistics is the second application, where we're trying to find probabilities through area calculations, and of course, area can be figured out using the integral. Now, this is more of a physics one, but work done by variable forces. It's basically integrating the area under the curve where you have force on one axis. And then the last one is signal analysis and engineering. So basically signal waves and other similar waves, and we're using this using area calculations and a lot of trigonometry. Now, the geometric application of volumes. This is another application, and it's slightly more complicated. So, volumes of revolution is what we have to do is we're calculating three-dimensional objects which are created by rotating two-dimensional curves around a single axis. So, there is a disk method. There's a disk method for things like circle or something that's close or something that's revolved around an axis and not multiple curves because everything's in circles. Then the washer method is for regions between curves, and the shell method is kind of very similar to the washer method, but you use it for rotation around the y-axis. The second one is volumes with known cross sections. Now, cross sections, if you've ever heard of cooking, it's kind of like cross sections of the meat, or cross sections can also be where you kind of like slice it up into a lot of circles and using that as cross sections at a perpendicular angle. Now, I know you might not understand that, but don't worry, these are all topics in integral calculus that will be covered in the future. So, the third one is multiple integral applications. So, actually, there's things that called using more than one integral, and that comes in multivariable calculus, but that's not as related to this, as this is only differential and integral calculus. Multivariable calculus, also called calculus 3, is a bit beyond this, but it's actually quite simple once you understand the basic concepts of calculus 1 and 2. Now, the last one is less pure math, but more engineering. So, engineering design calculations, which was really similar to something last video that we covered. Yes, and designing and analyzing three-dimensional structures using differential equations also, just as was covered in the last video. Then, so like fluid containers, structural components, and to figure out material requirements. So, for architecture and design, there are also a few more applications. So, there are four main that we're going to cover. Number one, which is load distribution calculations. So basically, we're trying to figure out how much force is here in the structure, how much force is there in the structure, and just trying to see how much of the forces are distributed throughout the entire structure. Now, the second one is also a physics one, is the center of mass determination, where we're calculating the point where a structure's mass is perfectly balanced. Now, if you want to understand center of mass, think about it like this. If you ever tried balancing a pencil perfectly on its side, now, if you have, you realize that there's one particular point along the pencil where it's perfectly balanced. Now, that point is called the center of mass for that pencil. Now, moment of inertia is a little bit different, but those two actually go pretty hand in hand, and center of mass is also sometimes used to figure out moment of inertia. So, inertia means resistance to force, and moment of inertia, we're trying to figure out some structure's resistance to rotational acceleration or torque. Now, the last one is to try to figure out a building's ability to withstand various forces like earthquakes or tornadoes or tsunamis or even hurricanes. Now, one field which you might not have thought was really as much of integral or differential calculus, excuse me, is geographic applications. Now, basically, what they're trying to say is we're trying to use integration to determine precise land measurements from survey points or like points along the land where we're kind of conducting our calculations. The second one is watershed analysis and water flow modeling. So, we're trying to figure out drainage areas and we're trying to figure out the overall water movement across different landscapes. Now, the third one is topographic mapping and elevation profiles. Now, a way to explain this is if you've ever seen those maps where you have red, yellow, orange, purple, and brown, and it shows and there's like a key where it says like this is this much height above ground. That's what called is elevation profiles or topographic mapping. Now, the last one is to optimize land use and infrastructure placement through mathematical modeling. Basically, we're trying to use integral calculus to figure out how to best use the land we have, and this is called urban planning and zoning calculations. Now, a physics application is work and energy. So, what they're saying is work is a force integrated over a distance, or W is equal to integral of FDS, or calculating the total work done by a variable along a path. So that's basically that, and work is also the amount of force times distance. So that's why ds, if you integrate that, that's F times S, where S is distance. The second one is we're trying to determine potential energy. And how much, so basically potential energy is energy based on the position or how much it's really stored. The same thing, it's kind of the opposite for kinetic energy, which is the energy of motion. And the last one is using conservation of energy, which kind of deals with things like analyzing systems where energy goes between different forms. So like kinetic, potential, thermal, electrical, and mechanical, which is just potential plus kinetic energy. Another physics application is fluid dynamics. Now, this is about calculating pressure and force, flow rate, Bernoulli's equation, and hydrostatic pressure analysis. So, for the first one is F is the integral of P dA, and the second one is Q is equal to V dA. Now, this is really relating to pressure and force, not just like how much pressure through the atmosphere, but also how much pressure water or a fluid exerts on another fluid. And Bernoulli's equation, as it says, is relating pressure, velocity, and elevation or position. The next physics application is electrical systems application. So what we're trying to do is we're trying to figure out things like total charge, the amount of energy to, and things like circuit analysis, which is kind of a combination of that, and also power consumption over time. For the total charge calculation and energy stored in capacitors, these are just straight up integral, but the other one also requires a little bit of extra background physics knowledge that doesn't really come straight into. Another more pure math application is probability, and the thing that we're talking about in probability is distribution function. So there are 4 function types: PDFs, CDFs, EVCs, and variance and standard deviation functions. Now, for the first one, PDS, we're basically just doing it as a basic function, f of x. Now, cumulative functions is f of t dt is, and you integrate that to get f of x, where f is capital. And this is saying the probability that x will take values less than or equal to that x value. Now, expected value calculations is basically if we take a random variable, what's the average or mean value of that? Now, for the last one, it's a more complicated integral, but it's a measure of something called spread or dispersion, similar to range, but it's slightly different. Another one which involves probability is statistical analysis. So, what we're trying to do is we're trying to use integration to evaluate claims, to evaluate ranges and spreads, to evaluate models, which was also covered in differential calculus, and something called Bayesian inference applications, which basically what we're trying to do is we're trying to integrate different and prior functions and functions that are quite likely to update probability distributions like the normal distribution. So that's really about it, and you can read the mini points if you want to learn more. But this is really just giving you a brief explanation and not going too in depth. This is more of an engineering thing, but it is about signal processing and continuous signals. So there's the total signal energy, there's not allergy, there's filtering techniques, there's Fourier transform, and there's signal reconstruction. So first we're trying to find out the total amount of energy. Now then we're also trying to figure out how to filter these to figure out the result we want. Fourier transforms, which is a different, more complicated topic, and signal reconstruction, which I actually really didn't know prior to researching about this. Now this is data analysis applications, which is kind of like a combination of pure math and applied math. So we're trying to analyze trends, we're trying to reduce noise and smooth data, and we're also trying to extract features. Now, of course, you can read the 3 mini points for each of these if you want to have a better idea of each of these. But the basic idea is we're trying to use integration to more like to identify patterns, filter and extract different things, and also to identify the things we want to extract and to figure out patterns. Now, a financial application is income streams. So this is not as much integration as there is also economics, but there is a present value of continuous income, future value projections, continuous compounding models, and cash flow analysis, which are kind of the 4 main topics that are really going to be covered in these financial applications. So that's really about it. And as you see, there are a few notes where differential calculus and integral calculus align, but normally this would also lead to the result of differential equations. So thank you so much for watching. See you in the next one, and bye.